All right, so we're gonna kind of open up on electrochemistry. Let me show you how this looks because the style of the problem sets is a little different. So usually this is the last unit we cover in the year. It's usually kind of rushed because it's at the end and we do it in a very kind of compressed way. But all the problem sets are based on one document that we just kind of keep adding to. So let me open that up and show you what it looks like actually here. So it's broken down into, I believe, 3 or 4 main sections. The first one is really just a review of things we did in the past, which is oxidation and reduction stuff. So that's what I was going to focus on today, just to kind of drudge that back up and kind of remind us what that's all about. Because underlying electrochemistry is oxidation and reduction reactions. So as you can see, we're going to remind ourselves what the definition is of these processes, how to assign oxidation numbers, um, predicting replacement reactions. This we might skip for now until we use the start learning about the reduction potentials, which will be next time. So this I might just wait on. But then figuring out what's oxidized and reduced, as well as oxidizing and reducing agents. And then, of course, our favorite, balancing redox equations. That was mostly the stuff we did before. Then, when we look starting next time, we'll start looking at electrochemical cells. What does that mean? How do we write them out? How do we show their function? What this really is, if you want to think about it, it's the chemistry of batteries in large part. So we're going to understand how something like the AA battery in your device works. How does it produce electricity? And then once we understand how chemical reactions can produce electricity, we're going to reverse it and get into things like electrolysis, where we can talk about how electricity can drive a chemical reaction. Now, what's interesting is as we're doing this, we're going to find ourselves having to kind of look back at equilibrium again, but we're also going to need to plug in some thermodynamics, which we haven't even done yet. But I think the timing will work because by the time we're getting toward the end of this, we'll probably be also getting to the end of the last unit. And so the stuff that fits together here will kind of coincide. And if it doesn't, we'll just wait for it. You know what I mean? We'll come back and finish it up. So really today I want to mostly just talk about, we'll just work through this together. So think of this as like the practice, but we're doing it together. And if you feel like you need more practice like this, as I said in this document, if you go back to Unit 2, it has all the old stuff we did already on this topic, right? So it has all the old problem sets, all the old notes and everything. Nelda, there's somebody in your house.
It's Talini. Do you want to say hi?
Oh, Tellini, put
Hi.
put your mask on. I'm just kidding.
Oh, sorry.
I'm just kidding. How are you?
I'm good. How are you?
Good. See what you're missing?
I know. Gosh.
I know. I knew she was so mean. Okay. Anyway, so let's see what we can remember from all this stuff. So how would you talk about oxidation and reduction? Like how would you define them? Do you remember? Somebody's chat. Oil rig, exactly. What does it stand for though? So we can actually like remind ourselves what it means. What is oil rig? Oxidation is loss, good. Reduction is gain. Of what? Electrons, exactly. So in chemical processes, one major class of reaction is this transfer of electrons. Sometimes it literally means forming ions. Sometimes it just means shifting electrons from one atom toward another. And so that's why the redox concept is a little bit broader than just saying like ions forming. But anytime there's oxidation, there also has to be reduction. Because if electrons move from one place, they have to go somewhere. So there's a very strong parallelism here between what we've just been talking about with acids and bases. It's just what's transferring is different. Hydrogen ions are transferred in acid-base reactions. Here it's electrons transferring. So as far as what that looks like, we had been learning how back then, or have learned, hopefully, not had been, but have, and will now be reminded of, how to assign oxidation numbers. So let's just try it first, and then I'm going to just kind of fill in the blanks as needed. So you're just like, well, I don't remember this, and I'll just, remind you. So let's kind of go with a problem here. So if we want to do assign oxidation numbers to all three elements, how do we do this in this first problem? So we have sodium sulfate. I'm going to write it extra big so it's easy for me to. So remember, there's certain elements whose oxidation numbers we assume we know, just because they're almost always in that state in a compound. Do you remember which were the key ones to remember? Let's kind of review the rules. Good. Oxygen is almost always -2, except for the times it's -1. I'll put it in parentheses, and that's just like peroxides. Hydrogen is almost always +1, except in those rare cases where it's -1 in what are called hydrides. And I don't kill myself too much over the exceptions because they're very rare. The one I would remember, though, for the peroxides is hydrogen peroxide. This one comes up quite a bit. So I would be especially aware of this one as +1 and -1 oxidation. And then remember, if it's a monatomic ion, whatever its charge is typically, and we can tell by the periodic table, remember the columns of charge, that's how we would assign those. And then, of course, let's put it this way. I usually write it in the other order. The sum of the oxidation numbers has to equal the net charge of whatever the structure is, the molecule or ion. And with that in mind now, we should be able to assign, because the sodium is an ion here, and we know it's in a +1 typical state when it's a sodium ion based on its position in the alkali metals. You've just reminded me that the oxygen's -2, and now really the mysterious one is the sulfur here. So let's see if we can work it out. Well, 2 sodiums means a total of +2 charge contributed. 4 oxygens is -8. And so we're missing a certain amount that will add up to 0. Since this is a neutral compound, this has to add up to 0. Well, you can see we're missing +6. And so the sulfur here is +6. So in this paper, or wherever you want to do it, on the side, whatever, the sodium's +1, the sulfur is +6, and the oxygen's -2. And just to remind you of my notation, on the top I'm putting the oxidation number, which is the per atom amount. So that's what we mean when we say the oxidation number. It's per atom. On the bottom, I'm kind of putting the totals, right? Like how much based on how many atoms of each there are. So just to keep in mind how I'm working this out. All right. What would you do for nitrogen in N2? This kind of adds that rule of a free element.
Isn't it 0?
Yes, exactly right. So if an element is in a state of not having been combined with any other element to form a compound, then it's 0. So that's exactly right. But in NO2, we have a different situation. What do we get for each of these? If you want to just holla, we'll put it in there.
+4 for nitrogen and -2 for oxygen.
That's right. And I'll just keep taking whoever answers, and if somebody has a question, feel free to chime in with your question. Here's the dichromate ion, a weird looking one. What do we do with this?
I think it's 12 for chrome, or no, 6 for chromium.
Good.
And -2 for oxygen.
Right. And just to show the logic there, because of this subscript, that messes it up. So this is -14 total. To get to -2, we need +12. But that +12 is shared between 2 chromium atoms, which is how we get them to +6. Exactly right. And then this last one just kind of shows one last weirdness in oxidation numbers. You have I3, but the overall charge is -1. And this gets to the fact of why we don't consider oxidation numbers the same exact thing as ionic charge. because what this oxidation number is could never be a real ionic charge, since each of these atoms would have to literally be negative 1/3, because we're taking that negative 1 charge and splitting it among 3 atoms. So even though this polyatomic ion has a charge of negative 1, the oxidation state of iodine here is negative 1/3. So that's kind of part 1. Like I said, we're going to not worry about this until we'll come back after we do the reduction potential concepts after next time. So let's move on down here and see what we can do. I'm just going to copy this whole chunk over and work through it with y'all. Throw in a new page. I find it's easier if I just keep dumping new pages in. All right. Wingdings. Well, it's easier until the internet starts to mess with my brain. Okay. So for a problem like this, we have to figure out what's happening to who. So we're just going to add an extra layer by assigning the oxidation numbers again, but this time figuring out how they're changing before and after. So let's see if we can kind of put the definition and the oxidation numbers all together to answer this question. And I spelled oxidized wrong. Oxidized. Whoops. And we did it again. What do you know? How did I never catch that? All right. So let's go through here. Let's do a quick run on the numbers first. So let's assign the oxidation numbers here. Let's see, -2, 8, 1, +7. If it's a charge, it's already known. If it's a charge, it's already known. If it's a charge, it's already known. So which of the elements was oxidized?
MnO4.
Well, that's 2 elements, right?
Oh, well, then Mn.
So you're saying Mn lost electrons?
My bad. No, that's wrong.
So what should it be?
O4, I believe. I think. No, wait. I'm wrong again. Fe.
I'll just let you guess everything. No.
No, I'm guessing everything wrong. Just ignore me.
No, you were right on the last one. I just want to make sure that you know why. Remember, when we lose electrons are negative, oxidation number goes up, right? It becomes more positive. That's what it means to become oxidized, really. So the iron starts at +2 and goes to +3 because it lost electrons. So the iron, and we have to be specific, it's this iron that was oxidized, right? The iron 2. Now what was reduced then? You're looking for the one whose number goes down by gaining. So again, we have to be specific and just focus on the manganese, right? Because it's the element of manganese that started in a +7 oxidation number, but it dropped to +5. And so that's why here, the manganese is what's ultimately reduced. Okay? Let's do the next one. Okay, cadmium 0, -2, +4, -2 +1. Ooh, hydroxide, so that's -2, +1. But the cadmium, so this is an ion of hydroxide, which is -1 overall, so this forces me to conclude that the cadmium is +2 ion. And by the same token, the nickel is also +2. And again, the oxygens are staying -2 and hydrogens are staying +1. So can you tell if anything changed, and if so, what? Like who's oxidized and who's reduced? Which one went up in oxidation number from before and after? Which one went up?
CD.
Yes, the cadmium went from 0 to positive. So it lost electrons, therefore it was oxidized. Oil rig. And then the reduction happened to the nickel, right? Because it went from +4 down to negative, or sorry, down to +2. And that's really all that section was reminding us of, being able to recognize it in context, because that is kind of necessary in terms of being able to then apply it later when we're balancing these redox equations. Any questions so far?
This we didn't talk about this, I don't think, but what do we call the thing that's doing the reducing or doing the oxidizing? Because isn't it like different than saying something is oxidized or reduced?
That's the very next section here.
Oh.
So this
Okay.
is the agent thing, is I think what you're referring to.
Oh, yeah.
Absolutely. All right. So in terms of agents, it's just like, oh, this is set up so we just keep adding a layer on top of the last thing, just layer after layer. This again. Sorry. Smarter this time. Okay. So again, in order to know what's the agent, we have to know what's oxidized and what's reduced. Okay, so once again, I'm going to go through and assign oxidation numbers. Methane's a little tricky. Let's see if we can figure this one out. What do you think? How would you assign the oxidation numbers here? It's just weird looking. I mean, it's not tricky. But we don't have any reason to think that hydrogen's anything but +1 here. So I guess that would be -4 to make it work out. This would be -2 +1, -2 +2, and 0. Now, when we look at the carbon, what happened to the carbon itself? Was it oxidized or reduced, just like we were talking about in the last section? Did it go more positive or more negative?
More positive.
Okay, so that's oxidation, right?
Right.
That means something better have been reduced. Do you see anything that we can claim was reduced? Another element?
The hydrogen.
The hydrogen. Now, it doesn't really matter which hydrogen I look at because the result is ultimately the same. They both start at +1 and they both end at 0. So now here's the agent thing, right? Agent means causer, right? It's a cause rather than an effect. So this is where we kind of had a pattern where we just inverted the word. So if something is oxidized, I'm going to write it like this too. I know it's going to look silly, but if I'm oxidized, I reduced someone else. That's how the agent thing plays in. So when I look at the methane, now I'm looking at the whole molecule, not just the element, okay? Because an agent is referring to a chemical agent, like as a whole. So when I look at the whole thing, I'm seeing that the methane was oxidized, so that means the methane has to be the reducing agent. Why? Because it reduced somebody else to become oxidized. In other words, my loss of electrons was caused by me giving the electrons to someone else, and that means I reduced them. And of course, by the same token, and I'll write it just to keep the notes complete, if I'm reduced, I love personifying chemicals, right? I oxidized someone else. And so in this case, we see the water being the other chemical in this reaction must be the oxidizing agent because it was reduced, and that means it had to be reduced by someone, in this case the methane, and if it was reduced, that means it oxidized someone else. And that's the essence of it. You guys want to try number 2 all the way through, and then let's see if we agree on what's what, and we'll see what we say. Got it? Or do you need more time, or let's compare notes? What do you think? I'll ask it this way. Which one did you say is the oxidizing agent?
Silver.
Silver. Let's see, does that make sense? I think you meant silver nitrate, because we're looking at the whole
Hmm.
substance, but I get what you meant.
Okay.
So it went
Okay.
from positive to 0, which means it was reduced, so it oxidized. Yeah, I agree. And then the reducing agent? Well, there's only one other thing here, right? So we got the first one right. The second one should be the copper metal here, because this one went from 0 to positive. Therefore, it was oxidized, meaning it reduced somebody else. And then, are there any questions on that, or is that good? So, go ahead, Zaina. The charges, yeah. So in this one, silver is a weird one because it's always +1 in compounds. The nitrate as a whole is -1. The copper as a free element is 0. Here, the nitrate being -1 and having 2 of them makes the copper +2. And here, the free element silver is 0. So really, the net ionic equation here is that 2 silver ions reacted with copper metal as a solid. Electrons were taken from copper and added to silver. That caused the copper to dissolve as copper ions and the silver to plate out as solid silver. So the basic movement of electrons was in this direction. And it was a total of 2 electrons transferred. And so you can see copper giving is reducing the silver. It's acting as an agent of reduction. And silver taking, its action is to oxidize the copper. Is that good, or? So then this last one, it's really similar. So again, zinc becoming positive means it's oxidized. So it looks like zinc is the reducing agent. And then hydrogen is being reduced. So the hydrochloric acid is the oxidizing agent. And that's pretty much that little chunk of concept. All right. So now the last bit, oh, your favorite, is the whole thing about using the half reaction method to balance a redox equation. I think we need to go through that again, at least once or twice. So let's put one up and just work through it. Oops, where am I going? This again. All right. So I can rewrite the steps to help you with this as I do them. Shudder. So the first thing we think about is the half reactions. So usually we just take the related materials and split them into half reactions. I'm going to write this in a really abbreviated way. So I can see the chromium must go to the chromium, and then I can see that the nitrate must go to the nitrogen monoxide. And I strongly urge you to start near the center of the line because you're going to build out on both sides, if you remember. And that will be kind of a pain if you start at the edge of the paper. You're like, uh-oh. So once we have the half reactions, we balance first anything that's not oxygen or hydrogen. Nothing here, nothing here, because the nitrogens are balanced, the chromiums are balanced. So now we're going to move on. The next thing we do is that we balance oxygen by adding water molecules as needed. Top line, no need. On the bottom line, though, there's 3 oxygens here, but only 1 here. So I need 2 more water molecules on the right so that the total oxygen is 3 on both sides. At that point, we're going to balance hydrogen using hydrogen ions. Again, top line, not an issue. Bottom line, the only hydrogen that we put in is because of the water we added. So there's 4 total hydrogens here, which requires 4 total hydrogen ions here. And then the last major step of the half reactions is that we balance the charge using electrons. I'm not sure how that says charge. Let me try that again. That's better. So now this is the part that is the first place where people really start to make simple mistakes. So you got to be careful here. So let's see, what color haven't I used yet that's available here. Okay, so on the top line, we can see right away that the left side is a total charge of 0. But right now, this side is +3. Electrons are negative. So the only way I can equalize the charges is to add 3 electrons on this side. Now both sides are 0. Down here, the right side is all neutral. On this side, there's 4 plus and a -1. So right now, this side is +3. So kind of the same argument, we need 3 electrons on this side. And now this becomes neutralized. So that's kind of the main first chunk. At this point, we have to balance the electrons, meaning the whole system. So in this case, there's 3 out and 3 in. It's already done, meaning that we already have the right number of electrons. Like if this had been a 2 and this had been a 3, we'd have to multiply the whole line of each by a number that gets them to the lowest common multiple. But here it's already worked out. So once we've balanced the electrons, or balanced the system if you want to call it that, then we add the half reactions. And that implies that we cancel things out or combine them as they can be. Main thing we're canceling are the electrons, because if they're still showing, we did something wrong. And then we just write in everything else. So I had 4 hydrogen ions. a chromium, gosh, squished. 4 hydrogen ions, 1 chromium, and 1 nitrate. On this side, we see the NO, the Cr plus 3, chromium 3, and then the water. And then quick check if it's right. Total charge is plus 3, 4 hydrogen, a chromium, an N, 3 oxygen, 3 oxygen. It's balanced. Ta-da! And notice the fact that we balanced it in acid is why we had water molecules as well as hydrogen ions available. Yes. So let's remember, if we're going to get to a basic solution, we do all the same stuff, but at the end we add in the hydroxides. So let me pluck one of those and let you guys work through it from the acidic side at least, and then I can help you with if you need the hydroxide part. So let's grab this one best. So I'll skip number 2. I'll leave that for you guys to try if you need to later. And I'll try to squeeze this one on the same page just so you know what? Come on, down here, please. Oh, I almost had it. Where'd the, aha, haha. Take it while you can get it. Why is life so hard? Here, okay. There you go. So I'm leaving the directions here so you guys can follow them. And you should be able to get it acid balanced at least. So let me give you a few minutes to do that. See how it goes for you, and if you get stuck, just ask a question. And once we're confident we balanced it in acid, we'll show how to transition it into base. Don't look up if you're not done. I'm going to start writing. And if you are done, watch for my mistakes. Three, three, six, 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 eight, two, two, four. And let's see if this works out. So 3 waters leave 1. I get 6 versus 2. Electrons are gone. 3 of these. 2 of those. 3 of these. And 2 of those. I think that did it. Oh, but he put it up there. I didn't even see. Yeah, looks like we agree. The 2 electrons where? At the top line? Because this side had a negative 3 charge, and this side had a negative 3 charge also. So those are balanced, but then we added these 2 hydrogen ions. So there was an unbalanced plus 2 on the right. And that's why the negative 2 had to be there. Yeah. All right, so if we're going to fix it into basic solution, now that we've actually covered some acid-base chemistry, this should make more sense than it did back then. But for every H plus, see the H plus is what makes it acidic, right? That has to go away. And if it's going to be basic, we're going to have an OH minus surplus instead, hydroxide. So to keep it balanced, I have to add the hydroxide to both sides, and I have to add enough to get rid of all the H's, with in mind, or in the back of my mind, remembering that hydrogen and hydroxide makes water. This is effectively what I'm doing. I'm just going to neutralize the acid now. But I can't just put it on this side because now I've thrown it out of balance. So I'm also going to add it to this side. But when I do that, these combine to make 2 units of water. But now I have water on both sides. So I can get rid of one of the water on each side. So in the end, all I've done is make that minor adjustment. It should still be balanced when it's over, if we did that right, but now it's in a basic solution because there's a surplus of hydroxide instead of hydrogen. So that's kind of the simplest way to do it, is just to do it like it's an acid and then adjust it to being in base. And that's really it. Now, all of these reactions, and I'm just going to kind of do a look ahead, imply that everything's in the same beaker reacting. And what that does is it allows the electrons to transfer directly from one element to the other. In other words, where the electrons are being transferred, they're in direct contact. Okay? I want you to think about this for a minute. If you want to give me a letter, you can come right to my house and hand it to me. Right, Amilda? Inside joke. Or if we're separated from each other, the way to do it would be to send it through the mail. And, it gets transferred through space to another place. So here's what's really interesting. We know, and this is just a look ahead, we're not going to get deep into it today, but we know if we look back at, I forgot I changed pages. Let's come back to this, where did I put it? Too many pages. Where was it? Yeah, like this one. So let me kind of zoom into, let's say, this silver and copper reaction for a moment. Actually, let me even make a simpler one. So consider the reaction, and I do this as a demonstration in class when we're in class, is that if I took a piece of zinc metal, we'll do zinc, and I put it in a solution of copper nitrate or copper sulfate, which, as we've known from the past, copper ion solutions are blue when it's copper 2. And I'll just put the copper. We know a redox reaction occurs, meaning that we can write a balanced equation that shows what we've already been showing. And this is the net ionic, so I'm leaving the nitrate or whatever it is, the spectator, out, just for simplicity right now. And the implication here is that there's a transfer of electrons from the zinc, 2 electrons in fact, to the copper. And the result of that transfer of those 2 electrons is to produce these products, right? That we oxidize the zinc and reduce the copper, and we would start to see copper forming in this solution. The problem with this is, although the chemistry happens just like we're saying, is we can't really tap into that energy flow unless, and this is the cool part, this is where this is heading, what if we separated the half reactions? In other words, we know that the zinc is becoming zinc ions plus the 2 electrons that it loses, and the copper ions are gaining those electrons to become the copper metal that we would find after the reaction. What if we separated them into 2 containers? So let me show you what I mean. So let's say we took one container and a separate container, like a beaker, let's say. And in one, we put a piece of copper metal. And in that solution, we had that same copper ion solution. Right? Before, the copper metal and the copper ion, it would all be in the same mishmash, right? They'd all be together. And on the other side, we put a piece of zinc metal and a zinc solution. Now, the electrons can't get to each other, right? We can't send the electrons to the copper yet. There's nowhere for them to go, is there? They're cut off. But what if we connected a wire, like a conducting wire, from here to here, and then gave them a bridge so that ions could flow back? Now we have a complete circuit. So here's the key. Now the reaction is still able to happen because we have contact between the same materials, but the difference is the electrons are forced to follow a path through a circuit that we've created. Instead of being able to directly contact and just kind of use up the energy in the reaction, what would happen if we put a device in here, in between, like a light bulb? Now we could light the light bulb because the flow of these electrons is basically an electrical current. That's the essence of how we're going to take redox chemistry, which interchanges between electrical and chemical energy, and be able to use the flow of the electrons to drive a process, to do work. That's really where this is heading. And so that's really, like I said, the basis of how batteries and things like that work. Chemical energy is used to make electrical energy. So next time, we'll start getting into those kinds of what are called cells and how it is used to generate electricity. We can connect resistors into a circuit like this, Betty. It doesn't tell us how resistors work, but even a circuit like this has a kind of internal resistance Because again, if we were in the lab together and I could show you that how you build the battery itself doesn't affect the potential if it's the same materials. Like you'll get the same voltage, but you will not necessarily be able to generate the same current at the same time. So in other words, it affects how well it generates power. Um, but again, this is all really interesting stuff that we could get into because, um, well, I'll just leave it at that. We'll wait till we get to it because if I just keep talking about it, you won't know what I'm saying anyway until we get to the nitty gritty. But it's just kind of cool that we can just by separating the parts of a reaction tap into the energy flow in a different way. And there's some theories, some evidence that even ancient peoples figured some of this out. Like there are instances of like what were thought to be solid gold statues from antiquity that have been found to be actually gold plated. So people were doing some kind of electrochemistry in ancient times, even if they didn't know exactly how it worked. There's even, and I don't know how verified this is, there's even some suggestion that the ancient Egyptians might have come up with a kind of rudimentary lighting system for under when they were building the pyramids, like in the caverns and within the pyramids, where they might have actually come up with ways to make some kind of rudimentary light bulbs and electrochemical batteries to light their way. I don't know if that's true, but I've seen that there is some evidence that suggests they may have had something like that. Interesting, but not sure. So this is going to be a little short session. I hope it was enough to get your beak wet with a reminder of electric or redox, enough so that when we come back next time we can do a little bit more with these electrochemical cells and learn how to build and analyze them. And there will be a simulated lab we can work through and see how it all works better. So, any questions? All right. Have a great weekend and don't forget to do your quiz for acid base. I don't even know what unit I'm in anymore because I'm teaching 7 at once, so it's all good. Take care, y'all.
Bye. Have a nice weekend.
You too.
Have a
Thank
great
you.